Hi everyone, this is Mr. Lee. In this video, we're going to go over potential graphs or potential energy curves. All right, let's begin. So on the screen, you should see a image of a bead maze. Now this is usually a toy for babies, but I'm going to be referencing back to this toy because the toy actually does a very good job of showing you what these potential graphs represent and what these potential curves represent. Okay, so if you hear me reference the bead maze, that's what it looks like. I'll bring one in class too so you can mess around with it. But it's a toy for little toddlers and toys for babies. All right, so let's begin by first going over the definition um, of work and force. So we know that the derivative of a potential function with respect to position, or the negative of that, gives you the F. Now keep in mind that this F is a conservative force. Okay, so any conservative force is anything that has to deal with potential. Okay, and the reason why I bring this up is understanding what's happening with the potential curves. You have to keep a couple of things conceptually in mind. One of them is that the F is going to be a conservative force. So if there's any outside force, that's not a conservative force. That's not being referenced here. Okay, so with that formula out of the way, let's actually draw a potential graph. Okay, so make sure you have a positive and a negative region. So that is potential in joules, and that's position in meters. Okay, and I'm going to show you a potential graph that looks like this. Yeah, then we'll do one of those. All right, so something that looks like that. All right, maybe that's the last part. So let's try it again. So there we go. All right. I like that one a lot. So this will be our potential curve. Now, a couple of things to keep in mind. The formula for force, or the conservative force, is negative du over dx. If you take a look, this du just means a change in potential. And we know that our potential variable is in the y-axis. So this is delta y over delta x, and x, of course, being position. And fortunately for us, that does represent the x-axis. So this is what we call the slope. All right. Now, we do have to be careful because there is a negative in front of it. So the negative of the slope gives you the force, or the conservative force. The conservative forces that we have dealt with so far is spring potential energy and gravitational potential energy. Okay. Now, when we relate this back to that baby toy, just keep in mind, because there's no springs involved, we'll be talking about the spring potential. All right. So let's go over the idea of slope first. Now, if we take a look at this section right here, okay, we can see that this section here, we have a negative slope. So what this means is that the slope is negative. So a negative of the negative slope gives us a positive force. And so if we were to take a look at the baby toy, okay, let's imagine that there's a bead. If we put the bead right here, okay, it has a certain amount of potential energy because it's at a height above zero. In order for the bead to go from that position, so we'll call this position 1 to position 2 right there, okay, what the conservative force is doing, which in this case is a force of gravity, is that the force of gravity will be pulling it along the downward direction. Okay, and so the reason why it's going to be positive is because if you remember, the definition of conservative forces is that it wants to make all things approach equilibrium. Okay, so if you're going towards equilibrium, that gives us a positive force. And so you might be wondering, in this for this graph, where would the equilibrium be? Well, let's go back to this image of the baby toy. So I'm going to redraw over the baby toy so you could see exactly what part of the curve we're talking about. So I'm going to be looking at that blue wire here, and I'm redrawing over that blue wire. Okay, so if you want to do a quick little sketch of this curve here. All right. So in terms of the red bead, okay, so if we have the red bead there, Okay, and the red bead is going from point A to point B, those two individual points. So this will be x1 and x2. The force of gravity is pulling the bead from x1 to position x2. And the equilibrium point will be the lowest part, okay, because all conservative forces want to go from high potential to low potential. Okay, it always wants to go from a high potential to low potential. So the fact that the force of gravity is pulling from high to low shows us that we can consider that to be a positive force. Now, if you push against this, that's where we will get the negative forces there. Okay, and so the idea here is if we were to have a bead, let's take a look here, from this position here to that position there, we can see here is our slope, and we have a positive slope. In the part that I just highlighted, I'm going to highlight it in orange so that you can see. So this portion right there, we have a positive slope. And so what that positive slope means is that the force is acting, the force will be negative, the negative force, because our slope or the force is equal to the negative of the slope. So what that shows you is that the force is going against. So the force goes against the motion, okay? Now, to be a little bit more specific, the force is going against from the high to low, because the object is going from low to high, and so that negative means that you're going against what nature wants, okay? Because the bead doesn't want to go from point 1 to point 2, it wants to go from point 2 to point 1, right? It always wants to go from high to low, but just because of the fact that you're going against it, that shows us that the force is going to be a negative force in that situation. All right, so we just went over what the slope represents, right? The slope is the negative of the force. Now we have to take a look at what the different parts of the graph can tell us based on the different problems that you'll see. So one of the things is we have to first be able to define total mechanical energy, okay? So the total mechanical energy is always going to be the kinetic energy plus the potential energy. Now, keep in mind, as long as no outside forces, ME initial will always equal to ME final, meaning that the total mechanical energy can never change. And so this is helpful with potential graphs because I'm going to do a quick sketch again of this potential graph. Something like this. Very good. All right. So let's say down here, okay, we'll say that this value here, what do I have in my notes? We'll say this is U is equal to -4. So right there, U is equal to -4. So let's say you have a problem, and the problem says when the particle has U equals -4 joules, the particle has a kinetic energy of 2 joules. Okay, so in this case, when you're given the potential and the kinetic, the first thing that you should do is you should figure out the total energy of the system. So the total energy of the system would just be U plus K. And in this case, it'll be -4 plus 2, which gives us a total energy of -2 joules. Now, the importance of this is several things. Okay. Now, let me first show you what the -2 joules represents. And if you have a different color pencil or a different color pen, I will bring that out right here so that we can see a stark difference. So here, let's call this line, this will be U is equal to -2 joules. That line is -2 joules. So what that line represents, okay, is that here, this is the ME. That line is ME of -2. So if you have a total energy of -2 joules and the potential is -2 joules, that means here, okay, U is equal to -2. Therefore, K is equal to 0 joules, meaning that if you have a total energy of -2 joules, at the point where your potential energy is -2, your kinetic will always be 0. Now, in a real world sense, okay, going back to the baby toy, right? In a real world sense, what does this mean? So here, this tells us a couple of things. This tells us that these are what we call turning points. Okay, when K is equal to 0 joules. So what I want you to think about is we're going to go back to that curve a little bit, but one of the problems that we did in class was a half pipe problem, right? So we had a skater on a half pipe. So we know that up here, we said that we had max potential. And whenever we had the max potential, we had kinetic energy of 0. Okay, and so that's what this portion of the graph represents. Whenever you have a kinetic of 0, you have max potential. And so for the skateboarder problem, we said that if the skateboarder starts up here, okay, the skateboarder, as long as there's no energy loss due to friction, the skateboarder will move down the half pipe. Okay, now down here, it has max kinetic, right, in terms of the skateboarding problem, but it goes from max kinetic and it goes back up, and that kinetic energy eventually turns back into potential energy up there until on the other side we have kinetic energy of 0 joules as well. And so the idea of turning points is that the object, one, it can never go beyond those points on the half pipe, okay, unless there's an outside force. The skateboarder, if there's no friction, will just go back and forth for infinity, unless there's an outside force. In the real world, we do have friction, and so over time, they won't go up as high, but we're working in a theoretical sense here. So the turning point idea is that whenever we reach a value of 0 joules, the object has no choice but to no longer keep on going up the potential curve, but rather to turn around and go back downhill, right? And so it goes back downhill and goes uphill, 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 uphill until it reaches this point up here, what has a kinetic energy of 0, can't go any higher, and then we go back down again. Okay, so this sustains the idea that your total starting energy is the most amount of energy that you can start off with. Now, in terms of roller coaster, we see this all the time. The very first part of the roller coaster, for any roller coaster, is a giant hill. So you're in a cart, right? And the cart pulls you up, 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 and then you're at the very top of the hill. You see a beautiful view of the park, and then there's like a couple of clicks, 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 right? Therefore, dramatic effect to really terrify you, and then you go down the hill. So this roller coaster is just a potential energy curve, okay? And then there's like loop-de-loops and all that. But what you never see for a roller coaster, okay? You never see the roller coaster go beyond the first hill. So first hill will always be the biggest hill. And that's because the first hill, you have the maximum amount of mechanical energy. Now, because it's a real world, when you're in the roller coaster, there is energy lost due to friction. And so, one, you can never go up back to that initial point. But if, in a theoretical sense, there was no friction and there was no energy lost, that first hill will be the highest height you can ever reach. Okay, but in the real world, because there's energy loss, you can never even get close to that initial hill height, because that is the biggest amount of potential energy that you can have. All right, so we just talked about turning points, and so in terms of vocabulary, you'll see questions about, where is your turning point. In order to figure out your turning point, you have to figure out when your kinetic energy is equal to 0. Okay, and when your kinetic energy is equal to 0, you have your total, or you have your turning point, and that can only come from figuring out your total energy or your mechanical energy. All right. Now, another part is what we call neutral equilibrium. Okay. Now, neutral equilibrium, you could think about what I like to describe as a ball on a table, okay, or any object on a table. Now, neutral equilibrium is right here along this flat part of the track that I will now highlight. Let's do this beautiful purple here. This is what we call neutral equilibrium. And here we can see that there's a long stretch where your slope is equal to 0. All right. And the important part is that you have a pretty wide area of constant slope of 0. Okay. So if you were to think about this in a real world, right? So imagine that you had a table, and let's say you had a ball. So if the ball is here, it has a constant amount of potential energy. And if you move the ball here, it also has a constant amount of potential energy. Okay, as long as there's no outside forces, the ball will stay on that table and it won't fall off. And so here we have a constant amount of potential energy. And so that's what the neutral equilibrium position represents. Equilibrium, of course, meaning that there's nothing extraneous. Okay, everything is adding up to zero. All right, now let's do two more equilibrium points. One part is called the stable equilibrium. And in this case, imagine like a bowl, okay, or like the half pipe. The stable equilibrium is like for a bowl, if you were to put like a marble in a bowl, okay, or for a half pipe, this will be the bottom of the half pipe. Okay, so for the marble in a bowl, when you put a marble in a bowl, the marble over a long period of time will eventually reach the bottom of the bowl. Okay, so the stable equilibrium shows where the object is the most, well, to put in terms, the most stable, meaning that nothing can really knock it out. Okay, so the idea is here at the bottom of these wells. So I'm gonna put this in red. So that part right there and this part right there. So a couple important things. These 2 points, if I were to add to my notes, the stable equilibrium has a slope of 0. Okay, so that's something that's coming up a lot. So even for neutral equilibrium, the slope is 0. Okay, and that's because the equilibrium, right? Equilibrium means that everything is canceled out. And if your slope is 0, that means your force is also 0, right? Your net force is 0. Now for here, this position here is called the stable equilibrium because if you were to raise the object up to this point, okay, it'll fall down, it'll go up, it'll fall down, it'll go up. But over a long period of time, we can just assume that the object wants to rest right there at the bottom. Okay, that's where the object wants to rest. And so here's another point of stable equilibrium right there. So I'll label it as SE. Okay, and up there is neutral equilibrium. So I'm going to label it as NE. All right, and the last point of equilibrium is what we call unstable equilibrium. Okay, so unstable equilibrium. Now, unstable equilibrium, you still have a slope of 0. Okay, but if you were to imagine unstable equilibrium, imagine like a water bottle. Okay, where if you push the bottle, okay, in one way or another, the bottle tips. The bottle tips over. And so because it tips over, it goes from a high potential to a low potential. So we go from high potential to low potential. But at the moment, in the moment of it just resting, for example, the water bottle just resting there, it is in equilibrium. But if there's any force, okay, there's any outside force, it will cause it to lose its equilibrium point. And so the equilibrium point for unstable equilibrium, it'll be right here. Okay, and if I were to continue this line so that we have a good picture, right, you could also add that as well. This right here will be unstable equilibrium. So we got to think about it. If we were to push, right, if we were to push this particle in that direction, okay, that particle will go now down this potential hill, or if you push it in this direction, it'll go down this potential hill. Okay, much like up here, if you were to push it here, it'll move down this way, and if you were to nudge it this way, it'll flow down that way. Okay, so at the moment, at that peak, it's in equilibrium, but any little nudge will make it go from a high to low potential. Okay, and the other important thing is that your slope is still going to be 0. All right, so that's how we read potential graphs. A couple of very important things to solve these types of problems. You have to be able to figure out the total mechanical energy of the system, because with that, you can figure out the turning points. The other important parts about potential graphs are the 3 different equilibrium points. So we have neutral equilibrium, which is like a ball on a table. Okay, we have stable equilibrium, which is like the bottom of a bowl or bottom of a half pipe. Okay, nothing can really knock it out of its equilibrium state. And then we have unstable equilibrium, where any outside force will make it lose its equilibrium status. In terms of physics. This is just how we view, just the world and what could happen to objects depending on the position and its potential. But whenever we get to the more theoretical stuff of physics, this stuff is pretty wild, and it helps describe different parts of quantum physics. And so it's pretty cool to know. Anyways, we'll get more practice in class, and I'll bring the baby toy in class, and hopefully can view the equilibrium curves in person and mess around with the beads. Okay, I'll see you next time. Bye bye.